These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you.
Not sure. How does a mixture question differentiate from, what's it called, an empirical formula kind of question?
I guess they both could be about the same, similar types of things. You could try to figure out empirical formulas. Well, in this type of mixture problem where they actually give you the picture, you don't need to figure out any empirical formulas because you can see them. Well, right. So the picture here is it says the oxygen is in gray. Does that really mean red? I guess.
I guess the other one's black.
Yeah, I guess so. Okay. So the nitrogens are in black. And the oxygens are in red. Okay, so the first point is that we have a box that has a bunch of nitrogen molecules and oxygen molecules, and they're showing that nitrogen is diatomic and oxygen is diatomic. So you're asking how is this different from empirical formula and molecular formula? Well, here they've just given us the molecular formulas. Right. Here we can see this has a molecular formula of N2 and this has a molecular formula of O2. So it's not like it's not like an empirical formula question where we're trying to figure out the empirical formula. They're basically just trying to test here whether you basically have a basic intuition for what happens in chemical equations. So first of all, they ask us what is conserved in this reaction. Well, would mass be conserved?
Yes, yeah. Mass is always conserved.
Based by common sense. If you start with 5 grams of stuff, you got to end up with 5 grams of stuff. It can't just disappear or add to itself magically. So mass would have to be conserved. How about the number of moles? The total number of moles, will that be conserved?
No.
How do you know?
Well, because some of the products could combine to make one molecule and then you have less
right.
moles.
So in general, the number of moles does not have to be conserved in reactions, but is the number of moles conserved in this particular reaction?
Yes. No, I don't know.
Well, let's say we kind of go through one cycle of this reaction, so to speak. How many moles of starting materials would be used up in one cycle, so to speak? Well, to go through one cycle, we would use 1 mole of this and 2 moles of this,
and
right?
That only produce 1 mole.
And it only produces 1 mole of this. So no, in fact, we're losing moles. Every time we go through one cycle of here, we use up 3 moles and only produce 1 mole. But you can't just assume for any of these problems that the moles won't be conserved. If the coefficients on the left-hand side added up to the same thing as the coefficients on the right, then that particular equation, the moles would be conserved. So you have to check that for each problem. But for this problem, the moles are not going to be conserved because we're using the moles up faster than we're producing them. So moles are not conserved. How about the number of molecules?
No, because they're recombining in new ways, so you're not.
It's really the same thing. We can interpret these coefficients as either moles or the number of molecules. Okay. So if we went through this for one cycle, we would say we would use up 3 molecules, 1 molecule of this and 2 molecules of this, and only produce 1 molecule of this. So this particular reaction does not conserve the number of molecules.
Right.
And how about the number of atoms? Will that be conserved?
Yeah.
Yeah, there's 2 nitrogens on the left and 2 nitrogens on the right. There's 4 oxygens on the left and 4 oxygens on the right. We're not destroying or producing atoms, we're just recombining them. So this is a problem where there was 2 different things conserved, and the answer was to pick both choices A and D, because this was choice A and this was D, and choice E was both A and D. So this would be the correct answer.
You know how there's always a conservation of mass? Is there always a conservation of atoms as well?
For chemical, sorry?
Unless they're going through decay, right?
That's a good point, which I don't think you guys have covered yet. So that's a good point. As long as you're doing a chemical reaction, the atoms will be conserved.
Okay.
The only time that atoms change is nuclear reactions, which you haven't covered yet. Yeah. So the atoms will always be conserved. And the mass will always be conserved. Although again, in nuclear reactions, mass is not conserved because it's changed into energy. But you guys are just studying chemical reactions so far, where the mass is conserved. Whether the number of moles or molecules is conserved, though, depends on the coefficients from the equation. All right, now the next question here was, what's the limiting reagent?
Nitrogen.
Isn't everything the same here though?
How would we figure out the limiting reagent?
Which is what you're given.
Yeah, so for this particular problem, how would we figure out the limiting
Well,
reagent?
you know that you need 1 N2 for every 2 O2, and you're going to have in excess of 2 O2s because there's only 2 N2s and there's 6.
Yeah, I think you're thinking about this well. Let me put that on the board a little bit more systematically, but I think you have a good intuitive way of thinking about this. What is the limiting reagent in words? How would you describe to a 5-year-old what the limiting reagent is in the chemical reaction? What does that term mean?
What there's less of.
Or what
exactly
runs out the most? What could
Very good. The limiting reagent is what you're going to run out of first.
Or what will produce the least amount of product.
That's true, because that is the thing you'll run out of first.
Right.
So the best way to think about it is it's the thing you're going to run out of first, which is not, so one thing is you're probably going to run out of the thing that you have less of. Here we only have 2 nitrogen molecules, whereas we have 1, 2, 3, 4, 5, 6 oxygen molecules. But it's not just what you have less of, but what you're using up faster.
Right.
It's true that we have more oxygens here, but we're using them up twice as fast. So you have to put those two things together with each other. Well, we have more than twice as much oxygens, and we're only using them up twice as fast. So it looks like you're right that we're going to use up the nitrogen first. But here's how to work it out.
That picture wasn't the same as the...
Oh yeah, I'm sorry, I should have specified. This picture is telling us the starting materials for this problem. You might see this type of question on the exam. They'll actually give you a picture where they draw the molecules that you're starting with. And so here's how I would actually figure this out here. So we have 2 moles of nitrogen. Well, let's figure out how much N2O4 we could produce from that. So what's the conversion between nitrogen and N2O4?
There's 1 mole of N2O4, 1 mole of...
Oh, then you would do the same thing with oxygen. You'd find you could make
6. Yeah, the conversion ratio here is 2 moles of oxygen for 1 mole of N2O4. That's how we use the coefficients from this equation. And as I think you already worked out, then we have enough oxygen to produce 3 moles of N2O4, but we only have enough nitrogen to produce 2 moles. So we're going to run out of the nitrogen first. So this is the formal systematic way that always works to figure out the limiting reagent. There's many ways to figure out the limiting reagent. This is my favorite. You already mentioned this. Ask how much product you could produce out of each of them. And the one that you can produce less product out of is the one that you're going to run out of first.
That's the answer to number 3 as well.
Yes, so the question is, what's the limiting, so what was the limiting reagent here? The nitrogen was the limiting reagent.
And there's 2 moles, or 2 molecules.
Yeah, and the third question is, how much product are we going to produce? Well, we're going to produce, actually I shouldn't have been saying moles here because we're just counting molecules. So I should have said this is 2 molecules, these should all be molecules. We're interpreting this in terms of molecules. And then we just figured out then we're going to produce 2 molecules of this. So this is one good advantage of doing it this way. It gives you extra information that might be useful for the problem. Yeah, so I think there's a good chance you might see a question like this on the test. And we just need to realize you're expected to interpret the picture as the actual number of molecules that you have.
Okay.
And then, so there was another one going
back
really
to quickly with...
Let me just point out one common mistake here. A lot of people make the mistake of thinking that that in this problem you're starting with 1 molecule of this and 2 molecules of this. But these numbers don't tell you how much you have. They tell you how fast you're using them up. That's a common mistake. This doesn't mean that you're starting with 1 of this and 2 of this. It's just saying every time you use 1 of this, you have to use 2 of these.
Right.
This is the picture that tells us how much we were actually starting with.
Okay.
Okay.